Welcome colleagues and intellectuals to yet another class or a lecture of the Medical Mental Gym lectures. With me here presenting questions, exam-focused questions on chemical bonding. I'll go through chemical bonding questions, so it's cardinal for us to have some background knowledge on chemical bonding. So without any further ado, let's dig into this. But one reminder to the watcher or the audience, we are asking if you would revisit and watch the previous video before, for we'll be solidifying the concepts that were stated on chemical bonding in this video. So without any further ado, let's dig into the work. Okay. So the first question we have presented forward is account for the increased electronegativity across the periodic table. Okay. So one word to answer this question will be what we're calling atomic radii. Okay. So atomic radii. Okay. Atomic radii refers to the distance, okay, or how many energy levels are between the nucleus of an atom and the outermost shell. Okay. So what we notice as we move from the S block of the periodic table to the D block of the periodic table is that this atomic radii reduces, okay, and we are to relate this to the increased electronegativity. Okay, so how this is pointing to electronegativity is that the closer the electrons are to the nucleus, the more electronegative an atom is. So atoms with small atomic radii tend to be very electronegative, and hence as we move from the S block to the D block, we are reducing the atomic radii, and as we move from the lower portion of the table to the upper portion of the table, we are reducing this atomic radii, and as a resultant effect, we see the increased electronegativity. Okay, so that's the first question, and it's been answered with a simple word, atomic radii. So as the atomic radii of an atom reduces, the electronegativity of this atom increases as well. So the reduced atomic radii will increase the attractive force between the nucleus and the electrons. Okay, let's keep those points in check. Second question. Find the maximum number of bonds carbon can participate in. Okay, so let's look at carbon. This is an atom. Let's look at carbon and its atomic number. So carbon has an atomic number of 6. So this carbon has 6 electrons in its outermost shell. If we try to draw up the electronic configuration of carbon, it will be as follows. So carbon will have an electronic configuration 2p2. Okay. So from this configuration, we can understand why and how many bonds this carbon is participating in. Okay. So let's look at the outermost shell configuration, and let's look at the possibilities of bonds from the outer shell configuration. So the final shell is the second shell. So we'll isolate all the orbitals in the second shell. So we have our 2s2 orbital here, which is filled with 2 electrons, and it must be satisfied because the s orbital can only occupy 2 electrons. And we've got the p orbital, which only has 2 electrons. And this one is unfortunately unsatisfied because it's got a capacity of 6 electrons. Okay. So we have a total number of 2 electrons in the p orbital, a total number of 2 electrons in the s orbital of the outermost shell configuration of carbon. Okay, so this is the outermost shell configuration of carbon, and carbon has a tendency of what we are calling expanding its octet. So carbon can expand its octet. And what we mean by this term is that carbon can undergo what we're calling sp hybridization. Okay, so how this will occur is that an electron from the s orbital is able to migrate and hybridize with the p orbital, the empty p orbital, and form a hybridized sp orbital, which will have 4 atomic orbitals with single electrons. Let me show an illustration of what I mean by this concept of expanded octet. Okay, so if this electron, due to the expanded octet, migrates to the p orbital, the empty p orbital, we'll realize what we're calling a hybrid orbital, which is sp hybridized, and it will have a content or a maximum of 4 atomic orbitals, which will be occupied by a single electron each. Okay, so if this sp hybridized orbital has single electrons, how many electrons then does this hybridized orbital need to be stabilized? Okay, so from your observation, to fill these orbitals completely, we'll need 4 electrons. So these 4 electrons will facilitate 4 bonds, and hence carbon is able to participate in a maximum of 4 bonds because of its expanded octet. Okay, so our answer has been given based on the electronic configuration of carbon, and the outer shell configuration of carbon has illustrated the expanded octet, and we have seen how carbon is able to form 4 single bonds. So carbon can form a maximum of 4 bonds. Okay, let's keep those points in check, because carbon is a cardinal molecule when you're looking at aromaticity. Okay, so as we move, these concepts will apply. So as we learn about them, let's understand them and be one with them. Okay. The third question says, what bonds are formed between metals and nonmetals? Okay, so let's take it back to our periodic table chemistry. Atoms that are known to be metals are positively charged. Okay. And atoms that are known to be nonmetals are negatively charged. So we want to establish a firm understanding on what bonds are formed between metals and nonmetals. Okay, so let me give a practical example of the molecule we're calling sodium chloride. So sodium is a metal, and chlorine is a nonmetal. Okay, so sodium has a single electron in its outer shell, and chlorine has a total number of 7 electrons in its outer shell. Okay, so the bonding that will occur between this metal and non-metal has to be facilitated by an exothermic transfer of this 1 electron from this metal, because it can lose this electron to attain stability. So the exothermic transfer of this electron from the orbit of sodium to the orbit of another atom, which is chlorine, is what we're calling an ionic bond. So keep in mind that an ionic bond will be formed when a metal and a non-metal are involved in a chemical bond. Okay, so the fourth question says, what type of bond is formed when 2 atoms share electrons equally? Okay, I'll give you a practical example of a scenario where 2 atoms share electrons equally. Here we have our diatomic oxygen, which in our Lewis structure appears as is. these two hydrogen atoms are sharing two pairs of electrons equally. There isn't a complete transfer of an electron from an atom to an atom, but there is an equal sharing of electrons between two atoms. And this bond is referred to as a covalent bond. So, a covalent bond involves equal sharing of electrons between two atoms. Alright, the beauty of chemistry is seen when we look at it from a chemical bonding perspective. So, don't forget to like, don't forget to subscribe, tell your friends about the channel, and produce more work as we enjoy the beauty of chemistry. Okay, let's look at question number 5. Question 5 reads, using the aid of a Lewis structure, illustrates an example of an ionic bond. Okay, so we use a Lewis structure to illustrate this ionic bond. The favorable Lewis structure I will use is Lewis structure of sodium chloride. So sodium itself has an electron, a single electron in its outermost shell. Chlorine has 7 electrons in its outermost shell. So, chlorine is a very electronegative atom. This means that chlorine has an attractive force towards electrons. So, it has a tendency of pulling electrons towards itself. So, when these two molecules interact in nature, they produce what we're calling sodium chloride. So this electron will be exothermically transferred from the radii of sodium to the orbitals of chlorine. So there will be a loss of electrons by the sodium atom, which will facilitate the formation of a positively charged ion. So this sodium in the Lewis structure will appear with no electron, the electron which has been lost, and a positive charge due to the loss of that electron. Chlorine, on the other hand, in the Lewis structure will appear with 8 electrons in its outermost shell, with an additional 1 electron which was gained from the sodium atom. So the gaining of an electron will be represented by a negative charge. And as we can see, this Lewis structure has shown us the formation of ions, hence the name ionic bonds. So we've drawn a Lewis structure illustrating an example of an ionic bond using the molecule sodium chloride. Next question states, what charge will an atom assume when it loses an electron? Okay, so you're very smart and congratulations for that answer. It's a positive charge because when an atom loses an electron, it possesses a positive charge. This is due to the relative electronegativity of an electron. An electron possesses a relatively negative charge. So, if we have accumulation of electrons, we have increased negativity. While if we have removal or loss of electrons, we have accumulation of positivity. So, this electron losing atom will possess a positive charge because the relative charge that an electron possesses is negative. Okay. Question number 7 says, how many pairs of electrons will be shared in a double covalent bond? So this question is asking for a covalent bond which involves equal sharing of atoms, and one specifically a double covalent bond and electrons to be shared in a double covalent bond. So I will illustrate an example of a double covalent bond between a diatomic oxygen molecule. So oxygen has 6 electrons in its outermost shell, and it requires 2 to be stable. So oxygen is able to form a bond with itself and share the 2 electrons it has with another oxygen, so that they reach a state of octet. As we have said, molecules want to reach a stable state. They always want to attain stability. So this oxygen atom will have a tendency of reacting with another oxygen atom to form a double covalent bond to attain stability. So this double covalent bond can be signified by these 2 lines. Each line on a double bond presents 2 electrons. So let me convert this to a Lewis structure, and this oxygen will have 1, 2, 3, 4. Okay. So each bond is symbolized by an electron from this oxygen atom, another electron from this oxygen atom, an electron from this oxygen atom, and another electron from this oxygen atom. This is a sharing of electrons. So the total number of pairs shared in a double covalent bond is 1, 2. So we have 2 pairs of electrons shared in a double bond, because each bond possesses 2 electrons, and 2 electrons call for 1 pair. So 4 electrons call for 2 pairs. Hence, this double bond has 2 pairs of electrons that facilitate it. Let's go to question number 8. Use the Lewis dot model drawing to show the structure of carbon dioxide. So let's look at carbon dioxide's chemical formula, which is CO2. So it's a single carbon attached to 2 molecules of 2 atoms of oxygen. So this carbon in Lewis structure appears in this manner. So each carbon is double bonded to an oxygen atom. This carbon is able to create a maximum of 4 bonds, as we have established in the previous work. So we utilize this property in stabilizing these 2 oxygen atoms. So carbon can interact with 2 oxygen atoms and form 2 double bonds with 2 oxygen atoms, and this will be a depiction of the product. So oxygen can appear in this manner. Oxygen reacts with carbon dioxide, with carbon to form carbon dioxide. Alright? So carbon dioxide in Lewis structure appears in this manner, each dot representing an electron. So what we've noticed is that our oxygen atom has attained what we're calling an octet. Our carbon atom also has attained what we're calling an octet, and our other oxygen atom has attained an octet. Hence, we've created a stable Lewis structure of the atom carbon dioxide. Question 9. In water molecule, which atom will have a partial negative charge? Okay, so let's draw the atomic structure of this water molecule. Water molecule has 2 hydrogens bound to 1 atom of oxygen. So here is one water molecule. Okay, so we use the concept of electronegativity to figure out the solution to this question. So our key point is to deduce the atom that's possessing this negative charge in this molecule. So when we look at electronegativity, we discover to say when you move across the periodic table, you are increasing electronegativity. Oxygen is in group 6, hydrogen is in group 1. From that analogy, we can tell that oxygen is more electronegative as compared to hydrogen. So the electronegativity will mean that it has a stronger pool of electrons. So if there is an equal sharing of electrons between this hydrogen and this oxygen, the oxygen will have more electrons drawn to its orbit. So this increased electron density of oxygen will give oxygen a partial negative charge. And hydrogen will have a partial loss of this electron because they have moved closer to the oxygen, giving them a partial positive charge to symbolize a partial loss of electron. So all the hydrogens will possess a partial positive and the oxygen itself will possess a partial negative charge. So the question to this answer is that oxygen is the atom which possesses a partial negative charge in a water molecule. Thank you, colleagues, for being attentive. For now, we'll end here. And in the next lecture, we'll look at exam forecast, questions on hydrogen bonds, and we'll look at their significance in pharmaceutical chemistry and their application in drug receptor interactions. So, thank you very much for being attentive. Please like and subscribe to the page. Invite your friends and loved ones to the page so that they understand the beauty of chemistry. See you in the next video. Shalom.